It is now time in our discussion to begin talking about a much larger number. The dozen may be a convenient way to measure things in a kitchen or maybe someplace else, but is not a good measurement in chemistry. Imagine being asked to get 12 atoms of sodium or 12 atoms of lithium. Atoms are so small that you can't even begin to see a dozen of them. So a scientist named Avogadro came up with a much larger number, and it's called the mole. This unit, 1 mole, is equal to 6.02 times 10 to the 23rd, a much, much larger number. It is equal to 6.02 with 21 zeros after it. So what's so special about this number? Well, it allows us to be able to deal with the size of atoms in a much better way, because this special number also is always equal to the atomic mass of every element. So let's look at carbon. Carbon has an atomic number of 6, meaning 6 protons, 6 electrons, but its atomic mass is 12.011. We could just round that to 12.0. So that means if I took 1 mole of carbon, I have 12.0 grams of carbon. But I also have 6.02 times 10 to the 23rd atoms of that carbon. Now I could ask you to go measure out 12 grams of carbon. That's easy. Just use an electronic balance. Let's try some examples. Let's look at sodium. I see it's got 11 for the atomic number, but it's got 22.9 for the atomic mass. So we'll round that to 23.0. Okay, so what does 1 mole equal? So 1 mole is going to equal 6.02 times 10 to the 23rd atoms of sodium. But what does that equal to in grams? 1 mole is 23.0 grams. I wouldn't ask you to go to the lab and count this many atoms of sodium. That would take 1 billion years maybe. But I could ask you to measure 23 grams. That would take a minute or two on an electronic balance. So you see how important the mole is. It allows us to function in the lab and measure grams and figure out how many atoms we got. How easy is that? Let's try one more example. 1 mole of lithium is equal to 6.02 times 10 to the 23rd atoms. But 1 mole of lithium is also equal to, well, let's take a look. What's the atomic mass? 6.941. Well, we can round that to 6.9 grams of lithium. See how simple that is. All right, pause this video and try the couple of examples I have for you on the worksheet. Okay, assuming that you have paused the video, let's take a look at the answers. Did you get them all correct? Here they are. Notice how each one has the same number of atoms, just like the dozen. All of them are 12. But every atom has a different atomic mass. One atom might be bigger than the other. Sulfur is 32 about, neon is about 20, and carbon's about 12. Now it is rare that we take exactly 1 mole of anything, and that would be true of our dozen. It's rare that you take 1 dozen of something. So how do we calculate things when they're fractions? Well, here's our triangles again, just like we did with a dozen. Let's see how these triangles are used. Let's say I've got 3.01 times 10 to the 23rd atoms of nitrogen, and it's equal to how many moles? Well, we go to our triangle here, and I would cover up moles. It tells us to take atoms divided by this number. So let's do that. That would be 3.01 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. Well, now these would cross off. They're the same thing. So I'm just going to kind of X those two off when we divide them. And I just have 3.01 divided by 6.02. So that's equal to 0.5 moles. All right, now what about if I want the second example here? If I want to go from moles to atoms. Okay, well, I will then cover up atoms. What does my triangle say I'm supposed to do? I'm supposed to multiply these two numbers. So I'm going to take 2, and I'll multiply that by 6.02 times 10 to the 23rd. So really all I need to do is multiply 2 times the 6.02, and then just write my exponent here. And that would be 12.04 times 10 to the 23rd. Now pause the video and try the other examples that I have for you and see how they go. Okay, again, assuming you paused the video, let's take a look at our answers here. So we see we got 2 moles of manganese here and 1.5 here for niobium. What about our atoms here? Well, we have 3 times a mole here, so that becomes about 18. And again, there's our exponent. We don't need to worry about exponents right now. It's always 10 to the 23rd. And this is 2.5 times our mole number to get 15 about times 10 to the 23rd. You're doing a great job. Let's finish up. Now what about our second triangle when we're dealing with moles and atomic mass? Let's try the example. We've got 2.5 moles of selenium. We want to know how many grams is that equal to. Okay, that means I'm solving for mass. And it says take the number of moles and multiply by atomic mass. If I cover that over. Well, I've got selenium right here. That's about 78.1. So I'm going to take 2.5. And I'm going to multiply that by 78.1. Okay, and that's equal to 197.5 grams. Now let's look at our last example. 27 grams of calcium is equal to how many moles? Well, let's see what our triangle tells us to do. I'm going to cover over moles. That means we take mass divided by the atomic mass. So now I'll take 27 and I'll divide that. Let's look at the mass here. And it looks like about 40.1. So divided by 40.1. And that's equal to 0.67 moles. So a fraction of 1 mole there. Which makes sense because 27 is less than 40. Okay, for the last time, pause our video and see how you can do on the examples provided. Assuming that you've paused the video here, notice how we have grams. We're going to take 3.2 multiplied by atomic mass to get grams there, and 4.1 multiplied by atomic mass in order to get the grams there. And here we'll be dividing by atomic masses. So you get 1.9 moles for the beryllium and 0.34 moles for the iron. Okay, so that's our moles part 2. And our next video we'll be looking at formula masses.